welcome to online tutorial videos from Matlab terminal. In this video, we will talk about fast terminal sliding mode controller and its Matlab implementation. Furthermore, we also do freelancing industrial project, provide online training, help in technical assignments, and other related work in the domain of control system, DSP, machine learning, and etc. For more information, you can mail us at matlabterminal@gmail.com. With this, we will start with the video. Firstly, what is a fast terminal sliding mode controller? As in this channel only, we have discussed the basics of sliding mode controller with its Matlab implementation as well as the terminal sliding mode controller. Now we will move forward to a more advanced version with this controller technique, that is fast terminal sliding mode controller. For that, first I would like to quickly recap that what is sliding mode controller. A sliding mode controller is a robust control strategy which makes any closed loop system robust under situation of parameter perturbation and external disturbances. What is the meaning of robust? Robust is that a controller is such designed that plant does not have any effect of disturbances or any parameter changes on the plant due to this controller. Suppose if a system is subjected to noise or external disturbances that can be of any kind, and the control action or the output is not affected by this type of disturbances, then the control system is called robustly stable. For that, we design a sliding mode controller technique, which is one of the popular robust control strategy. So for in this type of control strategy, we have system state. We in the reaching phase, there are two phases. In the reaching phase, we force system state to reach to the sliding surface, and on the sliding phase, we make sure that this system state remain at that sliding surface and finally reach to its equilibrium point, which is desired control action. So a sliding surface is plays very important role in sliding mode controller designing, because this is the main effect that make sure that the control system is stable or not. So sliding surface can be of any type. In this video, we will introduce a fast terminal type of sliding surface. A sliding surface is basically the functions of basically the function of system states. It can be of either power form, it can be of linear nature, and anything. In fast terminal sliding mode controller, it is a combination of both linear and terminal sliding surface. Linear sliding mode controller does not guarantee the finite time convergence of system states, while terminal sliding surface thus guarantees it. It means the terminal sliding surface is mainly responsible for finite time convergence of system states, but when initial states are far from their respective equilibrium point in terminal sliding surface controller, such type of sliding surface fails to guarantee the fast convergence. It means the terminal sliding mode controller provides the finite time convergence, but it does not guarantee the fast time convergence. So for that, we need a fast terminal type of sliding mode controller surface, which is a combination of both linear and terminal sliding surface, and it provides a fast convergence even if the initial systems are far from equilibrium states. So this is the main crux of a fast terminal sliding mode controller. Now in the general term, we consider nonlinear system. Suppose as x1 dot is equals to x2, where these are the system states, and x2 dot is g1x, that is a function of some function of x, plus g2 some function of x, plus hx into u. U is here control input. For designing any sliding mode controller technique, we have two steps. That is, first is to design the suitable sliding surface, and second is to calculate the control input that is applied directly to the system. So x is the system state vector, gx represent the uncertainties in system, and hx is a non-linear function of state vector. So for above, a fast terminal sliding surface is given by x equals to x dot plus ax plus bx gamma sine x, where this is the linear part of the sliding surface, that is a linear, and this is the terminal sliding surface, which we have already discussed in the previous video. So this is a we can say a general fast terminal sliding surface. Now for the Matlab implementation of fast terminal sliding surface, we have taken the system equation as same as in that of terminal sliding surface, that is x1 dot is equals to x2 and x2 dot is equals to x2 cube plus 0.1 sine 20t plus u, where u is a control input and x1 x2 are the system states. The sliding surface here we are taking is as the alpha x1 plus alpha x2, that is a linear, and x2 plus x1 3 raised to the power x1 raised to the power 3 by 5, where alpha is equals to 2. Now when we calculate the control input using invariance condition, which means if we derivate this sliding surface and equate it to 0, we will have some function of u, that is the u equivalent part, that is this minus 5 minus 0.15 sin s is also included in this u equivalent part, and the 5 sin s is the ud part, that is discontinuous effort, which makes sure that the system states in initial time reaches to the sliding surface, that is minus k sin s. So control input is minus 3x2 cube upon 2 minus 3x2 by 2 plus saturation uf comma 3 minus 5 plus 0.515 sin s. So now in the theory section, we have seen that we implemented a system for the fast terminal sliding surface. We have taken the example from this paper, that is on non-singular terminal slider mode control of nonlinear system. In this paper, they applied the terminal sliding surface, but we have included the linear part of the sliding surface here for with the same example. We can see in this example, that is x1 dot is equals to x2, x2 is the terminal type, and the u is designed in such a way. And the results, now we will take a fast terminal type of sliding surface in this. Now we will move to the Matlab implementation. For that, we have taken the first we will design the system, that is x1 dot is equals to x2. So we'll take an integrator here using continuous block. We will take the integrator here, and we need two integrator, that is because of x1 dot is equals to x2 and x2 dot is x2 cube. So we need two integrators here. So now that we have got the two integrators, we'll connect them. So x1 dot is equals to x2 simply, but x2 dot is this function of x2.1 sine 20t and u. For that, we'll take a summer here. So we have to take a summer. So for that, we will go into math operations and we will take a sum here. As it is a part of 3, and we'll connect it to here. So there are 3 terms that needs to be added here. So we'll change it into 3. First is obviously x2 cube. For that, we will take math operations and we'll go to math function. So this is connected here. So we have to change it into power. So now we have that here, we have got the x2, and for x2 cube we will take so from source we'll take a constant value and change change it into 3. And then we will connect this block. So we have got our first part. Next is 0.1 sine 20t. From sources only we will take a sine function, sine wave. We'll take a gain here. From commonly used blocks we can take gain, and we'll connect it here. Their frequency here would be 20t, that is 0.5. We can also, instead of connecting gain, we can convert its amplitude here. So we'll not take the gain here. So now the third part is U. For that we'll take a source, that is input here, and we'll connect it here, and we'll create a subsystem for this. So we'll take out variable, two out variable for x2 and x1. Here we have got the x2, this is x2, and here we are getting is x1, and here this is u variable. So we have successfully implemented our Matlab for this type of sliding surface. We have successfully implemented the system. So now we'll create a subsystem from this. We'll just right click and we'll create a subsystem. Then we'll move forward to designing the sliding surface. So the subsystem is now creating. Yes. So now we have got the this subsystem. So now we will move forward to sliding surface. We'll just now firstly we'll take suppose gain, and we'll just create a subsystem for simplification. So that we can directly apply its output, that is control input. The output of this subsystem will be control input, that is u, and we'll apply it to here. So we have got this, and this will be connected, and the output will be u, and the input of this subsystem will be x1 and x2. There will be two inputs. So we'll take another input here, that is this, and we'll just disconnect it, that is here x1, x2. So we have our two inputs, and we'll just connect them in from this. Now we'll design the sliding surface as well. So for the sliding surface to be designed, we have sliding surface as x2 plus x1 raised to the power 3 by 5 plus alpha x1 plus alpha x2. So first we'll take x2, x2 will take the summer value because it is a combination of 4, that is x2. First is x2. We can see in this that x2 plus alpha x2, where alpha is 2, so we will get 3x2. So we can directly implement it as 3x2 here. Output will be here, the output from here will be sliding surface. So now only the 3 terms are left that needs to be summed for getting a sliding surface out as output. For that we'll take three values. Here it will be 3 x2 plus alpha x2 is basically x2 plus 2x2 is basically 3x2. So 3x2 here. Now that is x1 raised to the power 3 by 5. So we'll take another math operation. We'll take math function here. Power, and we'll have this and another constant from sources, that is 3 by 5. 3 by 5. Now we'll connect this also. Now the only term that is left here is plus alpha x1, that is 2x1. So we'll take gain. We'll change it to 2x1. So now the output here is the sliding surface. Now for the system we need control input. For that we will have minus 3x2 cube upon 2 and minus 3x2 by 2. Firstly we'll design this, and this is the minus 5.5 sin s. So first we'll design minus 5.15 sin s. That is we'll multiply it with a gain. We'll take the sine function of it from using a math operation, and there is sine function here. So we'll connect this. This value is minus 5.15, and there will be a summing sign here. From math operation we'll take a summing sign. So now that we have got this part of the system, so now there will be four signs here. Okay, so we have got the last term here, and we have got it as control. Now we have done the minus 5.15 sin s. Now we will move forward to this minus 3x2 cube by 2, that is x2. So we will take a math operation. We'll take another math operation, and we have it here. We'll change it into power, and we'll take another constant source. We'll take another constant source from sources, constant. That is 3. Now we'll take a gain. And we'll connect it here. We'll just connect it here. This is here. That is minus 1.5. Now that we have designed minus 1.5 x2 cube, now that we have minus 1.5 x2, so we'll just copy this one. So now we have copied this, that is minus 1.5, and we'll connect it into x2. So now that we have got this, and we'll connect it directly to x2, then this part is done. Now only the saturation function is left. Basically, saturation function of this value, which is the derivative of this value, that is x1 raised to the power 3 by 5 into x2. This is the derivative of this, and we have to just multiply minus 3 by 5. So we'll take the derivative here. From continuous, we'll take the derivative of this value, and we'll have a gain here, that is minus 3 by 15. That is minus 3 by 15, that is 1 by 5. And finally we have got the control output. So we have successfully implemented this fast terminal sliding mode controller for this system. We are saving this value, and then we will run it. Now that we are running it, meanwhile this x1 dot, this sliding surface, we can see it is a combination of both linear and terminal sliding type of surface. We have not considered the initial conditions here, so that will be 0 0, the system. Now we will change the system equation once it has run this value. Running it, we have to make sure that this sign function is disabled, zero crossing detection, and all the power that we have used, it is also not signed. So now we'll connect the scope variables that we have not connected for system output. So we'll have a scope here for both system states. We'll change it into 2. Signal inputs. Number of input port, that will be 2 for both system states. Now we will save this equation, we will save this plant, and we will run it. While using signal function in Matlab SIMULINK, we have to make sure that we disable the zero crossing detection, otherwise we will get error for the same. Now we will run this code. We have run this code for only 10 seconds. As in this also the reaches to 1 second. So we have run this code for only 10 seconds. There was some error because we need to make sure that is this signed power, otherwise this function will give error. And also we have to update the system state's initial conditions as well. For x2, we'll suppose we'll take initial condition as 0.1, and for system x1 we'll take it as 0.5. Now we will run this code. The code is run here. So now we'll see the results. The output we can see that even if the initial states are very far, in this, just a second. So now that we have got the output, we can see the system state x1 is represented by here by yellow line. Even if the initial state condition are very far from the respective equilibrium point, the this system state reaches within 3 seconds to its initial its equilibrium state, that is 0 here. And we can see some chattering phenomena which can be finally removed by using another type of slide remote control strategy. And the system state here as x2, that is represented by blue line, that's also reaching in very less time to its respective equilibrium point. So thank you for watching this video.